the task and meeting. This I talk about the anomaly detection, and we have two hypotheses. This one used for the it's in the previous session I spoke about the, for example, anomaly detection. This is the original version of the anomaly detector.
I mean, was X equals to?
Yeah, this is the two hypotheses here. In the first hypothesis, we have only for example, background noise. But in the second one, we have a signal plus a background.
Then it's not.
Yeah.
But for hypothesis testing, you can only say x equals to n or x not equal to n. You cannot say they are not like numbers. If they are not equal, then
Because this is a noise and we don't have any information about noise, maybe we have some statistic of that.
yeah. But if you do hypothesis testing, you can only say you can only reject h0. You cannot say h1 is correct.
Yeah, it doesn't matter.
Yeah.
It doesn't matter.
As
Here. That's right.
and here we suppose all of our data are in the matrix x1, xm, and each of our data has x1 and xm.
Can you repeat the notations?
Yeah, this is all of our data. We have n number sample or data, and each of input data has 1 to p coefficient. Yeah, some data something like this. Here p and m. M is the number of the data, and p is the number of the. For example, in the hyperspectral, it's the number of the spectrum that we capture. With the kernel tree, yes. We define something to use the kernel tree to change this equation to the kernel space or feature space. If you can remember, we had and here the C is the covariance estimated covariance matrix, and the estimated mean of the data, and here is again the mean and variance matrix in the feature space, and we use some calculation, and for example we expand the C as as eigenvalue V, eigenvector, and eigenvalue transpose. And again, for the eigenvalues, we thinking that's xb xb is the eigenvalue, the eigenvector are the linear combination of all of the data in the kernel space. Here x b phi is the phi x1 to phi xm, then and if we exchange this value here and again here and do some multiplication, we reach to KRT minus K mu BT KB minus 1 at KRT minus KT mu B. We calculate this value and this value, and from the original data we try to find the k between k. If you remember, this big K was equal to kernel of, for example, x1 to kernel of x1 xn, and yes, and this value again, if you remember, it's for estimation the KB here we need to have a centered or unbiased data, and create the unbiased data is need to, for example, find the value of the each point in the second space, and for example do a calculation and find the mean, and and after that subtract the value of mean from the original data, and based on this new data we try to find the covariance matrix in the second space. If you remember, I used the equation something like this: k b hat is equal to kb minus 1 m over m, kb minus kb multiplied 1 m over m plus
Okay, what's K again? KB and K.
This one,
Not KB, you have a KB also.
KB hat,
KB. R.
KR.
KR.
R is the point that we observe. And the meaning of the K, okay, let me write it on this thing before. KR T is equal to okay, this one is the one row or column of this matrix minus the mean value of that column. It's created KRT, and we have K mu V mu hat B T. This one is equal to 1 over n sigma k x I x b minus 1 over n2 Okay. This one is the mean of each column minus the mean of all of the data in this matrix. And if we calculate these two value and put it here, we can these two value. This one is equal to phi r x b at b, and this one is mu hat b phi we doing the multiplication between these two and keep this value in the middle as KB hat inverse. We do the multiplication between these two and find this value, and this two and find this value, and these two are equal, and transpose of 1 multiple to the here KB hat. Okay. I think it's clear. And
So like K mu B transpose.
K mu B transpose is the multiplication of mu B phi multiple x B phi. Okay. C B phi is equal to eigenvector V phi. Okay.
You first decompose the C and multiple the first term with
Yeah.
the first eigenvector matrix and then the second term.
Yeah. And again, this one is equal to, instead of this x b phi big B K transpose XB phi transpose. Okay, and here this one multiple to first term here, and again this one multiple to second term here, and we keep this one as K hat B minus 1.
I mean, your lambda is the same lambda or what? The
This-
second
this-
is lambda B also?
Yeah, lambda B, yeah. And the B is the matrix that's provide the linear combination of all of the data to make a eigenvectors.
B is the coefficient matrix. B.
Okay.
I mean, because you said it's combining the all x to form its eigenvalue. For B.
Eigenvector.
Oh, eigenvector. So B is a coefficient and times the lambda times the B y is equal to K.
Yeah, because I can. This one is equal to x b big B, and this one is x b big B. Big B is a two-dimensional matrix to okay. I can write that B is equal to beta 1 to n, and each of betas are again a matrix by J. Yeah, one of okay. And here we need to, for example, find this unbiased version of this matrix. For example, if we want to find one coefficient from this one coefficient I of K I J hat is equal to phi centralized x I transpose phi x j. C means phi. For example, x minus mu.
So is it also equal to K?
For one coefficient of this one.
Yeah. Is it also equal to K x1 x x3?
Yeah. This one is Kij. Equal to this one. And this one is K I J hat.
So this should be equal to element in that matrix.
Yeah.
But what's the difference with the KB and KB hat?
In the KB, you find the kernel version between x1 and x2, but we need the kernel value between x1 and x2 minus the mean value, because it must be biased. It must be the mean of this data must be equal to 0. And finding the mean in the second space is not easy because we need to move all of the data one by one to the second space, find the mean value, and after that minus to this value and make a Kij. And if I replace this value here, it's equal to phi, for example, xi minus, instead of mu, it's the summation of phi I1 to n transpose to phi xj minus again mean value of phi of this one, for example, I can do t and t, this one is t equal to 1 to m phi x xt. Okay, instead of this one, this term, instead of this one, this term, and after multiplication it must be phi xi phi xj minus phi xi sigma t equal to 1 and phi xt minus equal to 1 and phi xj plus t1 equal to 1 to n equal to 1 to n phi xt1 phi xt2.
Where is it, this transpose? The first term is the transpose for the first term.
Yes. The mean value doesn't matter to the transpose because you find the value, one value for a vector. Okay. This one is k xi xj okay. Here we need to find the multiplication of one value of xi multiple to mean. If we want to find how we can find this value from this matrix, it's equal to 1 over n. Excuse me. Here we have 1 over n because it's the mean and okay, it's the mu, and here we have 1 over n and 1 over n squared. Okay. This one is equal to finding the one specific term multiple to all of the data. It can be, for example, sigma of 1 and is the kernel version between xi and xt. Okay, it's equal to finding the summation of one row. Okay, because you want kernel version of one multiple all of the data. For example, the specific a specific row that is the kernel of, for example, phi xi multiple to xt. This is the one row of this matrix, and if we want to find that, we can. It's the summation of one k xi xb and the display y is the one from 1 to let me change the notation. 1 k xi multiple j from 1 to n. Okay, now it's one row. Okay, yeah. One row of this matrix. Okay, and for this one,
should be transport. This is
yeah, and this one is 1 over n. I equal to 1 to n k x I xj, and this one is the one column, summation of one column in this matrix, and for this one is
how do you get this thing?
it's multiplication of this term to this one is this, and this one to this one. Yeah. This one. Okay. And here is okay, and this one is the coefficient in this matrix, and for finding this value we can do a summation on one row. It can be equal to multiplication of ones matrix m by m ones. If we do a multiplication to the k and the matrix version is equal to kb, this matrix, minus 1 over n once n multiple to kb. Okay, because it's create a, if for example we have 1, 1, 1, and we have, for example, another matrix A, B, C, A2, B2, C2, C3, if you do the multiplication first row to first column, it's A1 plus A2 plus A3, and this is the summation of one column, okay? And if we move the ones here and do again the multiplication, if it's A1 plus B1 plus C1, and this is the summation of 1, okay? And minus 1 over n, JB once n, and here is the summation of all of the coefficients in the matrix. If we have, for example, A1, B1, C1, A2, B2, C2, A3, B3, C3, and here we have the ones, 3, and ones, 3. If we do first multiplication, we have a matrix. For example, 3 by 3 is A1 plus A2 plus A3 for all of these two are the same, and here B1 to B3 and C1 to C3, okay? All of the value in the column are be A1, A2, A3, okay? And if again the multiplication to the ones, it's create a summation of one row, and that is the summation of all of the value in the matrix. And plus 1 over n2 ones n kb ones n. And for this middle value, for this middle value, we assume that CB5 hat is equal to okay, let me start from here. We have the eigenvalue and eigenvector. If the eigen value multiple eigenvector phi is equal to CB5 eigen vector, it's equal to 1 over n summation of the phi center of xi multiple phi center of x I transpose. This term is for the CB multiple D5. Okay, because for finding the variance matrix you need to multiply all of the data. And this one is equal to 1 over n sigma of 1 to n, 1 to n, eigenvalue of phi c xi v phi multiplied v c v c xi. Okay, and
How do you get this one?
this value multiplied to this value, this is the coordinate matrix, okay? And this is the column vector, okay? And if I change the order of this two multiplication, because this one is it's created 2 by 2 matrix. For example, we have a multiple to this one. Okay, the result is this matrix, and for this one, it's
Because the phi c transpose v is a scalar, so you can move scalar in front of the phi c mu I.
yeah,
So you get the same thing.
yeah, yeah. That's true. Okay. For here we assume the phi v phi is equal to xb xb to the big beta is here I can rewrite it as v phi is equal to sigma beta I multiple to phi c of xi for all of xi, which we write it down as x b phi bit beta bit b. Okay. This is the from PCA on the data. If we want to find the eigenvalue and eigenvector in the kernel space, we can multiply one phi c xn here and one here, and if we do the multiplication, the lambda beta I equal to 1 to n of phi c xn multiple phi c xi. Here the phi xn is for all of the data we wanna multiply all of the data again in this part. N equal to 1 to n. This one is for this term, and for this it's equal to for this term.
How do you get the first beta I?
V phi is the multiplication beta I to phi xi. Okay. And here we multiply phi c xn. Okay. And this term is equal to, for the second one, it's equal to 1 over m, I equal to 1 to m beta I phi c multiplied x n phi c x I phi c x I transpose sigma of phi c x I. Here n equal 1 to m. And I can rewrite it as m 1 over m beta I, the multiplication and the kernel value of c x n and sigma j equal 1 to m phi c x I, this is the scalar, multiple to the kernel value of phi c x I x j and phi c x I. And here we have the again KB, it's the multiplication, it's the kernel value of all of the value, and if I can write it in a closed form as lambda m lambda B is equal to K B beta. Okay. From the PCA in the original space, we had C B phi is equal to B phi lambda B phi transpose. And here K hat B is equal to beta, for example, omega KB and beta transpose. And we know these two values must be equal, this side and this side are equal, and because we know the combination of xb multiplied to big B is a v phi, we can find the value of big omega B is equal to 1 over m kb. And based on this, we can calculate the value of kb minus 1 because we need it on the equation of
Trying to do it again. That's not lost already. What are you trying to do again?
I try to find this value that shows the eigenvalue and eigenvector of the KB in the kernel space or the some we can find it. If we find it, it's n times of the eigenvector of the max version.
So it's KB or KB hat, like the eigenvalue of KB or KB hat.
All of them is KB hat. I use something that changed everything to KB hat.
Yeah.
Everywhere if I miss something is KB hat.
Okay.
Because here is the, I think here I missed this KB hat. Because it says phi centralized unbiased. Everything is KB hat.
So beta I is you try to decompose V5 to 5 CS spaces, right? Then how do you get what to below there again? And
This one,
yeah.
okay. Multiply this one to phi CXN, where the n is 1 to n. Okay, by multiplication of one term here, multiply all of the data to this part and this part. We can change this whole thing to this one.
And write down steps. Can you write the steps?
Here, this one is the KB.
Before the lambda times sigma, the first step. You said you multiple something.
Here,
Yes.
okay. Here we have V phi theta. Okay, phi theta is the beta phi c of xi. We multiply phi c of xn where n is equal to 1 to n. Okay, change this part to the kernel value. Okay, it creates again k hat b. Okay, and here we have a k hat b here, and multiplication of this term to the some value, and again k hat is create k hat b b theta big b, and n is this. Prepare some code if you want to see the result.
Oh, where's that? I want to look at this one. So how to step from one to the other, like why can help B is equal to that mass there?
Which one?
How to translate that to like M naught of B, like
have one term here, KB. Okay, and again here we have two term KB because we have one KB here.
So what's KB again? I forgot.
KB,
When you say 5CXI, this one is equal to
KB
IJ
is,
or what?
yeah, KB hat is, it's a matrix K, for example, K, let me write a K1, 1 to K1M, and KM, 1 to KMM. And I explained how to change the original KB to this one.
Yeah.
Okay. And based on this, we have one here. And one
I mean,
here.
what's KB hat is equal related to 5C? What's the relationship of KB hat and 5C?
This is the for 1 to m. All of the xi, the kernel value of all of the xi to kernel value of all of the xn. Xn is again 1 to m. It's this matrix.
You want to say like 5CXN, 5CXI, the inner product is
Yeah.
one way.
For example, you
and
can. This one is I and this one is n. N is from 1 to n and I is 1 to n.
That would be equal to 1 sum over the whole, right? You have one KB is actually cancelled, right?
Yeah.
Like that.
Yeah.
I think you need to write down that step, no one can follow that. Yeah. It's impossible. I read that paper, but now I remind me, but no one will be able to follow. You need to write down that step to prepare.
Okay.
It's
Here
impossible to follow.
we have one KB as K lambda B multiplied to K hat B is equal to K hat B K I think 1 over n. One over. And this 1 over n here, and this 2k we cancel. Because here we have again a KB.
So this term comes from this lemma
Yeah,
5C
yeah,
vaccine transport.
yeah.
So you guys can know that.
Yeah, yeah. But this one is the multiplication of this term.
Notice one line really step for this one.
Yeah.
I mean, you should like expand this like summation there, and then put these two terms here, and each of these become like KB. This now is like KB and I. This is a matrix, and this you really should kind of need to. Seriously, no one can follow them. I guess it's impossible to follow. This become constant or somewhere, I guess. And sometimes it's J, I C, X I. So this is like A, B, and I. This is a A, B, J, I, something like that.
Yeah.
This have a, yeah. So therefore you have a beta I in the middle. So when the summation goes like, you have J, I, J,
I and J are the same. All of them are 1 to n and create a KB.
Wait, this is that. Is it flip or what? Is that like KB? Is that symmetric? Or
Yeah, symmetry.
Okay, the symmetry is symmetric also.
It's symmetry. Yeah.
So that I can think of like I am here. So this is like B multiplied by KB. But that is which element is that? This should be the n. But that's the whole. Wait. Beta I is a vector.
Yeah.
Okay. So you got a whole row for that.
It's one column of big bit.
One column here. So yeah, something like that. So I get the whole column of the. This is symmetric, therefore it doesn't matter. This KB is symmetric. Here is also symmetric. So yeah, this should be a sound transport. Yeah.
Because I multiply the XCN here.
If you multiply XCN,
Oh, so everything is a column vector?
Okay.
Yeah,
I-
you should
I-
have a transport.
Yeah, I multiply from this side.
But you still need a transport. If everything is column vectors, you have a transport. It doesn't matter. But yeah, lots of this. Let's forget the KB there, just write K. So K, basically K is symmetric. K, therefore I can write K n I is equal to K I n is equal to this thing, like phi. Let's forget the C also. Phi n phi I. So the last one is basically just like beta I. I and so there's a matrix here, some over I, 1 to m. So beta I is a column, it's basically a column vector. So you have this is like this multiplied by, so when we get back this the that I get back a column here. So this is basically the nth column of this. This is equal to beta k as a matrix, the nth column of that.
Yeah.
I don't know how to write it. Nth column. So let's write MATLAB notation. So it's like an angle like that. So and this here, so you should pull all this summation out here. So like this I1 and this J1 and so beta I here. So we have this phi n, phi I, and this is the phi. So this is a constant, so we can pull it out basically. Oh no, from here, this one to here.
This
No,
one is
this
from
okay.
here.
Oh, here is like from here.
Yeah, it has two sides. This side we calculate here,
Okay.
and this side we start from here.
I thought that's equals that.
Yes, that's why you skip this also. That's very confusing. So yeah, I want to go through that myself. So here you have when I need to step back to see. So you have V5 is out here. He use here. He use here to multiply, and then this substitute into V5 there. You use this one and then substitute V5 into this one here, and then also to
here.
here,
Yeah.
also to here, and yes, and then we multiply this by C transpose
Yeah.
to everywhere,
Yeah, 5C and
transpose
from
everywhere,
here.
and then and sum over that. And then therefore he has this and that and then the last step is we have this by C6. This is JI there.
Here, you want somehow got the 5 transpose 5, so you need to substitute this in the product this term, so you can get this in the product list. So you replace this in the product by K.
No, actually, the objective is that you want to get this, and then get this and get that equation here. Like here you get basically this side already, and then like here you will get this here. So then you can cancel this TD here.
So this is actually 5 times.
No, you could
We don't have any
No, this is just a long, this is a constant.
constant.
Here's a
But there's a down there.
Yeah. Is that matrix is a value?
This is a column. Yeah, okay, yeah, this. This column. And then I in the middle, I have okay, and oops, why? This is beta I also. Is there something wrong here? I have too many I indexes. This is some
This one.
yes, but this is some of the what? I think you
I.
have
Only
you,
have I.
here you solve for I again. So you have some index problem. Here you sum over I, right? Then you sum over this again, use I index again.
Yeah, this one is
One
for
of
this
the,
part.
yes, I know, but you cannot use this index twice. Here you have an I here already.
Okay, I use J here.
So did you change the index here? Right? So this index, some of them should be J, is not I anymore. You remember to change that? There are too many I's, definitely not right. No, but you don't want to do full I, right? It doesn't make sense, right? No, I mean, it's okay, but once you put them together, then
Yeah.
you need to change the index.
Yes, J.
Yeah, but did you change them to J
J.
also?
All of them.
He is more correct. Like you have N, then this one is J, this is I.
Yeah, I see J,
But this is not
J.
So that makes more sense. And this has a J here, and then NJ and JI here. and there's some I here. I can, oops, but still like some of a chain and I. So my page have to be
Big I.
on that side. So actually I have to move a bit I here. Maybe I have this K, I, J, like that instead. But I need to have J, M.
I think IJ is equal to JI and put this here.
I know I is equal to J, but I need to put that like order like that. You have this I is outer.
I think the order is reverse.
Yeah, actually here I have some I is the second index. Wait, what? I is the second index here. If I need to do some, then I will get the beta KB. It's not good one. You need to be careful with this kind of stuff. You need to play with wool, not just the wool is like when you have matrix model. Okay, now I write like that, this all becomes scalar. I can shuffle that one, but if I need to make sure it's a reasonable matrix multiplication, I need to make sure the second index I have the first index. You can shuffle it one whatever you want, but then I need to shuffle in a way that, like, for example, for this one, it should be something like Ij beta. Yes, actually. If I have a beta I here, Ij. After someone who got that with the J column of the okay, you agree with here? I mean, if you agree with that, like something's
Here, the beta CNI is equal to beta JD. And here, beta I.
no, it's okay. I'll finish this. Yeah.
This is an example. I assume it was vector and random vector, and n equal to 100 and j equal to 5, and randomly I add 1 to 10 column of that vector and assume it's the anomaly, and try to find the non-kernel version and kernel version of the anomaly detector. In the non-kernel version, I find the mean and with some technique I subtract the mean of all of the values, and here I estimate the value of Rx in the column matrix that the diagonal of that is the value of Rx, and in the kernel version I try to create a matrix of all of the kernel values here, and after that mean and KRT and KMUT and K hat its value, and I use different kernel function. For example, here's the exponential of the differentiate of the two input values, and if I run the code, the value of 10 and the anomalies are detected on these points. You can see the point is 50. The points that I chose for the anomaly, for example, here first one is 55, and you can see the value of the 55 is bigger than the others, and I can run it for multiple times and different kernel function. For example, I can change the
What's the blue line? Curve?
the blue line is the non-kernel version of Rx.
Okay.
And they can't find where is the point of the anomaly. Okay. The differences between values the points are very close to it, but with the kernel version the value are far from, for example, the points that are anomaly from the others. And for example, I can use
Suppose the original input is like
the random vector
how many
100,
dimension is 100?
100 number of inputs, but dimension is 5.
5.
I can change it, for example, to, and you can check it, for example, I can put 40.
That's okay.
This is the value if the input dimension here is a 4. Any question?
y-axis? What's the y-axis?
The value of output of the
R.
R6.
So the smaller.
The smaller points are anomaly because they are far from the others. For example, 10 number one, 10 point here are the anomaly, and the data that's noise in the around 2.5. Yeah. I add something to all of the spectrum. Maybe we can assume, for example, randomly select some J's to put some value on that. But here, because I add to all of the value of one column, because of this, it's easy to detect by the
Have you compared the performance of different kernels? The performance of different kernels.
What do you know about performance? You mean speed or
The accuracy, can you fix the seed, then change the kernel and you see if you find the same point?
yeah. But in this data is not, it's a fake data and more.
Yeah, I mean, even it's fake data, you can still fix the seed and then try different kernel.
Yeah.
I see the output of your algorithm.
Okay, you mean I fix the C?
Yeah.
In this example, each time I calculate the C based on the input data. It's not a fixed C.
I mean, if you given a seed, then the input vector will be the same for different simulation. In this case, you can change your kernel, then we can see
Yes.
if the output are different or not.
Yes. I didn't do something like this, but I can.
You just add a seed here.
You mean
You found out. Yeah.
you mean the coherence matrix?
No. I mean the seed of the random
Okay.
number.
I didn't get.
I don't think you don't have to put the seed one like just
Because
do you put any seed way? Wait, what on yeah, that's what I'm thinking. So it's just every time you really it doesn't know what it's generating.
Yeah, I mean, if you want to compare the performance of
Well,
different kernel, you should give it the same input.
I guess you probably should just repeat it many times also. You cannot tell like if your input will be biased to one particular kernel every